All right, let's begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray to be with us. Help us to just understand what we're doing. Give us clarity of thought. And let's pray you again help these students as they work on this course and others this semester, Lord, that they just take every day to glorify you, Lord. In your name I pray. Amen. Oh, wait, so I don't want you to get the wrong idea. I don't usually believe in handouts, but since this is math, I make an exception. This is a proof of the multivariate integration theorem, which is very similar to what I wrote, but it's just the rest of the thought without me butchering the punchline of it. Ooh, watch out for the water. Here, I'll just give you guys a stack. You need to hand some to the row in front of you, too. But, well, anyway, I don't want to say anything more about the proof because I'm very capable of getting confused about it again right now. So let's not do that. But anyway, here's something to read. Another voice on the matter. This is from Susan Culley's Vector Calculus, which is a really nice Calculus 3 only book. And if I had my druthers, I would use this book for this class, but I was told that you already spent like $30 whole on your calculus book, so we can't make you buy another one. Oh, I'm sorry, that's off by an order of 10, right? $300. Behind you. Behind you. All right, so anyway, basically, this is the argument that I went through, just with a little bit more nuance and the whole idea, hopefully. So you can read that. That might help make sense of what we did yesterday. With that, upon request of Mr. Vu, I am going to attempt to calculate the volume of a three-sphere. How do you calculate the volume of a three-sphere? Well, we've talked about, bless you, we've talked about double integrals. We talked about triple integrals. Could you talk about quadruple integrals? What would a quadruple integral be? What's a three-sphere? Yeah. So, in other words, we want to calculate. Basically, let me just use letters here: dx, dy, dz, dw, and x squared plus y squared plus z squared plus w squared less than or equal to, well, let's say r squared. This would be this three-sphere. So this, let me give this a name. This is the three-sphere of radius r. It's a subset of R4. Last class, what did we do? Among other things, one of the things we did last class, the sphere, well, excuse me. I really shouldn't say that that's the, I'm thinking of the solid sphere. Maybe I should say B3 or something. I don't know. Let me say B3, because I do like to think of S3 as just being the edge of things. Like S3 would be equality, all right? For example, I think this is a good notation. S2 is xyz such that x squared plus y squared plus z squared is equal to 1. So this is the so-called two-sphere, the one you're most familiar with, right? But the solid sphere, I might call B2, right? Same thing, but what's the difference? Less than or equal to 1, right? So solid, the edge, two-sphere, solid two-sphere. So the question I'm posing is, can we calculate the volume, or, well, it wouldn't be volume, right? It would be hypervolume of the solid three-sphere. How did we calculate the volume of the solid two-sphere yesterday? What do we do? Yeah, we're gonna need, right. Yeah, so let me just call this thing D4V, it's the four-dimensional volume, or the hypervolume element. There is a there's a change of variables theorem. The proof is almost the same as the one I gave you, or didn't give you yesterday. And that's you do the quadruple integral over the transformed region, right? And what you have to calculate is the determinant of the Jacobian of x, y, z, w with respect to your new variables. And the new variables are going to be rho, phi, theta, and another one, psi. What do you want? You don't want me to do psi?
No, I'm just trying to pronounce it right.
How about we'll do alpha there. You happy? Alpha's easier for me to write anyway. And this will be d rho, d phi, d theta, d alpha. That's the change of variables theorem. So the unpleasantness would be actually calculating this. This is a 4x4 determinant. So the first thing you have to do is to come up with sort of the next level up of spherical coordinates. How would you? I mean, I'll start us out. We've got x is rho, and that's going to look a lot like what we already did. Cosine theta, sine phi, y is equal to rho sine theta, sine phi, z is equal to rho cosine phi, and then w is equal to rho times something. And so what we need, right, is we need some way to get these to what do we want? We want that x squared plus w squared plus z squared plus, we want the sum of x squared plus y squared plus z squared plus w squared equal to what? Not 1. This is an identity for the coordinates. We want it to equal to? What is it? Yeah, for this one it was rho squared, right? Also rho squared here. That's our goal with these formulas we're trying to invent right now. So I'll get us started. It seems like the last thing must be cosine alpha. Right? I know that if I take x squared plus y squared plus z squared in its current form, what does it give you back? Before I write what I'm about to write in blue. What's just in the black, if you square x, y, and z and add them together, you get back, from our usual arguments in spherical coordinates, we get back rho squared, right? So if I just multiply each one of these by what? This w squared gives us what? W gives us rho squared cosine squared alpha, right? I want something to modify these formulas so that I get back rho squared when I add them together, yeah? Right, but I want a sine squared alpha to be produced from x squared plus y squared. No. You were right. Sine alpha. You just put sine alpha. Sine alpha. Right. So that gives you x squared plus y squared plus z squared is rho squared sine squared alpha. When you add that to rho squared cosine squared alpha, bam, you got x squared plus y squared plus z squared plus w squared equals rho squared. Theta is very special. There's only one angle like theta. But if you go into higher dimensions, if you want to make natural spherical coordinates in higher dimensions, you just keep adjoining like additional phi type angles. Additional polar angles, right? Because it's off the z pole. So, what's that? Nope. These will work. And the integral is from 0 to pi, because these both go from 0 to, oh Oh, why'd I put them in that order? That's yucky. The next one was what? This one was 2 pi. That's the theta one. The phi goes from 0 to pi again, and rho goes from 0 to r for our region. So, all you got to do, right, is calculate the Jacobian for this transformation and integrate it. I suppose I could burn 30 minutes of class time doing that, but I think we probably could do better things. I just wanted to set it up for you. Now it's straightforward what you have to do, right? You have to calculate this thing right here, right? Should be the determinant of x rho, y rho, z rho, w rho, x phi, y phi, z phi, w phi, x theta, y theta, z theta, w theta, x alpha, y alpha, z alpha, w alpha. I have worked this out before. I don't remember it off the top of my head, but if you want to work through it and see if your answer is right or not, I can tell you, okay? If you would like to work this out and hand it in, it's worth 5 bonus points. So if people who do that problem apparently get 5 bonus points. Dang it. Luke, I saw you drop your Aikido. I'm not sure you're prepared for such comments bring upon you after class. Sorry, we're looking at your transcript, and like, Professor Young was looking, he saw you'd signed up for that. He was like,
I had a lower grade in Aikido. I had calculus too. I knew it was time to switch things.
I stand by my decision, my personal decision to take bowling for credit only. That would have been a bad grade. I forgot a very important thing. You need to do really bad at the start of the course, right? Because it's based on improvement. I bowled my best the first day of bowling, and then it just went downhill from there. Every technique they tried to teach me made it worse. Okay, anyway. Now that I've got that out of my system, phew, my goodness, no wonder you guys were paying attention. I should have known this was a homework problem. Well, now the mysteries of the universe are clear to me. All right, so are there any questions about homework or anything? Go ahead. And then the green pig, no. X, Y. What does this notation mean? What does this notation mean, though? I can't tell from this. Is this like, you must mean that's Y, right? These are Y bounds? You're asking me to evaluate a function of 2 variables, right? So you must tell me if the evaluation is being done with respect to X or with respect to Y. Otherwise, I don't know what it means. Surely with respect to Y. So yeah, that's X squared minus 0. Mm-hmm. Is there an error in my notes or something? Oh, okay. All right. Any other random questions about how to evaluate things? This is interesting. The diversity of questions today is really astounding. Yes.
Can we do a determinant that is 4 by 4 but is not that? Just so we can do a determinant like that?
Yes, we could do that. 4 by 4 determinant. So suppose I wanted to calculate the determinant of 1, 0, 0, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I will be boring. I will simply show you the expansion in cofactors across the top row, or the expansion by minors as it's sometimes called. So what you do is you pick a row or a column. I'll pick the top row. Here's 1. So I do 1 times the determinant. And then what you're looking for is everything that's not in that circled entry. So the everything else that remains is this what I've done in red, right? So you do the determinant of that. 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. Then the way the determinant works, it's very plus-minus-y, okay? It's anti-symmetric. Anyway, so then you do minus 2 times the determinant of everything that's not in the in the 2 row or column. So that would be this stuff here, right? And this stuff right here. That would be what goes with the 2. So I get 0, 0, 0. Good news. That means it's 0. 6, 7. No such wonderful news will be present for you in the calculation of the volume of the 3 sphere. It's maximally non-trivial, that example, in some sense. I mean, that's a hard calculation. That will actually increase your computational stamina. All right, so 3 is the next thing. It goes plus, minus, plus. We're back to plus again. It's really just like the thing we do for cross products, just keeps going. So for 3, that would be these 2 columns and this column, right? So I get 0, 0, 0, and 5, 8, 11 from my second column, and 7, 10, 13. You guys with me? I hope. And then we have reached the next one, 4, which I'll make exploding. So that gives me minus 4, because I go plus, minus, plus, minus. We're back to minus again, 4, determinant. And then I need everything that's not in the 4 spot. So that's 0, 0, 0, 5, 8, 11, 6, 9, 12. Reading off columns, which is weird, but I did it. That's a year. Actually, it's not so weird. I've learned recently something called the VEC operator, which is based on reading off columns. Anyway, I will not digress. Now, there's a wonderful thing about determinants. If you have a 0 row or a 0 column, it's 0. So if I'm actually going to finish this calculation, we can do it pretty easily, because this is 0, this is 0, this is 0, because of the 0 column. So I actually only need to calculate this one, which then we're back to our usual bag of tricks. So it's 5 times 9 times 13 minus 120 minus 6 times 8 times 13 minus 110 plus 7 times 8 times 12 minus 99, whatever that is. I don't really care what it is. That's the answer. So.
You'll have to do it for 1 row.
Mm-hmm. Yes, sir.
And that whole thing is multiplied by 1. I understand.
Right. Yeah. So, I mean, that's important, because if it's not 1, if it's something else, then that's still there, yeah. Like for this, it would be cosine theta sine phi sine alpha, multiplying the first one and so forth. Like I said, it would take me at least a half hour of class time to calculate it. And I'd get it wrong. It does simplify down pretty nicely, though, at the end of it. So, by the way, guys, I don't think I talked about this much yet, but so we found that dv. Oh, sorry, it's not time to talk about that yet. Never mind. Getting ahead of myself. The comment I was about to make is for surface integrals. We're not there yet. So other questions? Let me look at an example then, if there are no questions. Let's see if we can't calculate the triple integral of the square root of x squared plus y squared dv over the, let's say, Jawbreaker, 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4. I call that a Jawbreaker because it looks something like this, right? But three-dimensional. It's between, it's sort of a three-dimensional annulus in some sense, right? It's between those two spheres. So how would I do this? What kind of integration chain should I use? So 3 of these pages are the proof, but I threw in, since I was going to use 2 pages anyway, on the last page, I threw in the take-home message from yesterday. Here's how you do the polar integral, and here's how you do a volume integral, right? So you got your Cartesian, your cylindrical, and your spherical volume elements. What change of variables scheme do you want to use here? You have 2 competing things, right? Square root of x squared plus y squared, well, that's a cylindrical thing, right? That comes just to us from the world of cylindrical coordinates, right? But the bound is quite obviously spherical, right? So I think the way to go here is I think I'm going to go spherical on this one, right? That means the integrand will be a little bit of trouble, but the bounds are super easy. What are the bounds? When you translate these into spherical bounds, what is this in terms of spherical coordinates? This is just what? Two, yeah. Yeah, in physics we tend to use R. I almost exclusively in here use R when I'm doing coordinate change problems for the polar radius. But it is true we have used R for the radius, like the position vector in other discussions. It's just notation. It's an unfortunate thing, but it is what it is. So 0 less than or equal to theta less than or equal to 2 pi, right? You sweep all the way around. There's no restriction on the angle. And then the phi also goes through its natural range. So I would say that in terms of spherical coordinates, this is like a rectangular solid from the viewpoint of spherical coordinates, right? The bounds are constant is my point. So this just becomes integral from 1 to 2 integral from 0 to 2 pi, integral from 0 to pi. No particular reason I'm choosing these orders except that I just wrote them that way over here. It really is not significant, that choice. And how do you rewrite r? Now I have to write the integrand in terms of spherical coordinates. What is r in terms of spherical coordinates? We talked about this yesterday also. R is rho sine phi, right? So I do rho sine phi, and then what's my dv? dv, the volume element rewritten in spherical coordinates, is rho squared sine phi, and then I got my coordinate differentials, right? So d phi, d theta, d rho in my current ordering. And then I just integrate, right? So there's no dependence. So first of all, the integrand factors into separate functions of r and phi, and thetas, there's no theta dependence at all. And the bounds are constant, so I can just multiply integrals here. I've got what? I've got rho cubed d rho from 1 to 2. I hardly even need to write this, right? I mean, a lot of times when I'm doing a problem like this, instead of writing this, I will just write 2 pi. That makes sense? I mean, the theta integral integrates to 2 pi here. And then the interesting one, I've got myself a sine squared phi, d phi, that I'm going to have to work on. Yep. So my point is that that's r. R is the square root of x squared plus y squared, but it's also rho sine phi. How do you integrate sine squared? Let me rephrase that. You need to be able to integrate sine squared. So remember, sine squared phi is 1/2 of 1 minus cosine of 2 phi. So the integral of this is just what? I mean, I get what? I get 1/4 of 16 minus 1 times 2 pi times, what's the integral of that? It's what? It's 1/2 1 minus 1/2 sine of 2 phi evaluated from 0 to pi. I did a u substitution to pull out the half, right? Where's the 16 coming from? That would be rho to the 4th. 2 to the 4th is 16. 1 to the 4th is 1, right? This piece dies. Yeah! Because you have sine of 0 or sine of 2 pi. Those are 0. The only thing that matters is the half. Whoa. Oh, I'm sorry. You guys, don't let me get away with that. Does that 1 belong there? What's the integral of a half? Is it a half? No, not 0. What belongs here? Not 1. Phi. Very good. So when I evaluate that from pi to 0, I get pi over 2 for this. So I get 15 over 4 times 2 pi times pi over 2 again. So the answer, it looks like, is 15 pi squared divided by 4. Can you think of any ways I could change this problem a little bit and still make it a reasonable problem that would be interesting to do? What if I just said z was greater than 0? Let me make a list of some modifications we could do to this problem. Number 1, if I also impose the restriction that z was greater than or equal to 0, what would that tell me? 0 less than or equal to phi less than or equal to what? What's the xy plane? It's phi equals to pi over 2, right? So that would change the phi bound to pi over 2. Interestingly enough, this is still 0, and it just makes this pi over 2. You just, by the symmetry of the problem, you get a half of this.
Yeah.
What if I did instead that we're looking at the same thing, but just with x and y greater than or equal to 0? What would that enforce on us? How would we impose that in spherical coordinates? That basically means you're in the first octant. You take the final answer and divide by 8, you say. I think you're exactly,
If it's only in one octant, it's 1/8 of the whole thing.
I'm sorry. To make Mike right, let me add a z here. Z, x, y greater than 0. So if z is greater than 0, we still need the 0 less than or equal to phi less than or equal to pi over 2 to get z greater than 0. How do we impose x and y greater than 0 in spherical coordinates? This is what? This is theta equals to 0. This one over here is theta equals to pi over 2, right? You're sweeping between those two things to keep x and y positive, right? So you just do 0 less than or equal to theta less than or equal to pi over 2 as well. And Mike is right. Changing this to pi over 2 cuts this in half. Changing to that to pi over 2 changes this 2 pi to a half pi. The net result is division by 8. Absolutely. Cool. In spherical coordinates, z is equal to rho cosine phi. Let's look at a different problem, if you guys don't mind. I probably still need to go back and do some more tricky double integrals. But I just feel like doing triple integrals at the moment, so I'm going to do some more triples. How about this? Integrate, goodness gracious, how about this? X over the square root. How about x over x squared plus y squared? No, excuse me. I'll make up my mind eventually. Square root of x squared plus y squared. Integral. dv. Over the solid region S, where S is defined as follows. It's bounded by x squared plus y squared equals to 1, and z is equal to 6 minus x squared minus y squared, and also z is equal to 1 minus x. There's the problem. So the first thing with any of these problems is to come to terms with the volume that you're facing, right? We must gain understanding of what it is we're actually integrating over. So x squared plus y squared, that's easy to understand. What's that? Yeah, that's a circle. And if you have that independent of z, it's a cylinder, right? Now, of course, in cylindrical coordinates, that's just r is equal to 1, which is kind of nice. I tell you, once I see something that's bounded by a cylinder and other stuff, I might immediately jump to, I'm almost certainly going to use spherical, spherical. Duh. Cylindrical coordinates. Now, 6 minus x squared minus y squared. What's that do? That it hits this at here at z equals to 5, right? And then it kind of domes up like that. So the top point here would be 0, 0, 6, for example, right? So I can, just kind of ignore that's part of it. That's the top of my shape. What about z equals 1 minus x? What's that look like? It's a plane, right? And see if I can get a picture of it. If this is x, and oh, good grief. If this is y and this is x, z equals 1 minus x, what's that look like? It's where does it go? Let's see. When x is equal to 0, z is equal to what? So it's like right here, right? And 1 minus x, so it's kind of like, I can't draw it worth anything, but I made 1 too big. Let's put 1 down here for the sake of my picture. Oh, my picture is horrible. I have put the x-axis over here for my convenience. Anyway, I can't draw it worth anything, but sufficient to say it's some kind of slice down here. The plane is going to form the bottom, right? Where does the plane intersect? Let's see. This does what? If x is what's the largest negative value x can take on the cylinder? -1, right? So the biggest z can be as it intersects the plane is 2. So this point up here is going to be at well, my picture's wrong, obviously. That would be, I guess it's the opposite way. Oh, no, it's not. This is at, sorry, I'll get it right eventually. This would be at actually, you don't have to draw this picture that carefully. I'm just drawing a little bit more to try to convince you that this is what we're looking at. And on the other hand, if x is equal to 1, that would give me 1, 0, 0. That's actually, if I had drawn it better on the x-axis. So my picture, don't take too much of my picture. The point is, it's pretty clear, though, would you agree, that this plane is below the parabolic top here. That's the main point. The point I'm trying to get across here is that 6 minus x squared, 1 minus x is less than or equal to z is less than or equal to 6 minus x squared minus y squared. That's true for each point in the bounded region, which I'll foolishly try to shade now. It's something like this. Just that thing. Now, this is much easier. This is actually 1 minus r cosine theta less than or equal to z less than or equal to 6 minus r squared. And theta goes all the way around. And what's r do? 1, right? So this I can do as the integral from, let's say, 0 to 1, integral from 0 to 2 pi, integral from 1 minus r cosine theta to 6 minus r squared, right? Now, what is this? What's that? Cosine theta. Very good. And the dv? Right. And then I have to do corresponding to my bounds, dz, d theta, dr. Right? Now, the z just integrates to give me what? Cosine theta times 6 minus r squared minus 1 minus r cosine theta times r d theta dr. See what I did there? The z, again, this z integrates to give me, dz integrates to give me z, and so I have to evaluate from this minus that. And, oh, no way. Huh. Let's see here. So we've got like an r times 6 minus r squared cosine theta minus r cosine theta plus r squared cosine squared theta d theta. I'm pretty stoked about this formula. Why do I like this formula? I'm sorry, should I say it's sweet? What is the correct vernacular of your generation? Stoked? Okay. I don't know. Depends who I'm talking to. I don't know. Do I have the life experience to use the term sweet? I don't know. Maybe it's incorrect for me to use that term. I don't know. Let's see here. This, 0. 0. You integrate cosine from a whole cycle, it's 0. I don't need to write any more. Those terms go away. Cosine squared is what? It's that, right? And this piece also will integrate away. If you go over 2 pi, that piece integrates to 0 because it's going over 2 cycles, right? That has period pi. So the only thing I actually have to care about is the half in the cosine squared. And so this basically just boils down to integral from 0 to 1 of 1/2 times 2 pi from the theta integral. And I got myself r squared dr. So that gives me pi divided by 3. Yup. I'm sure you could find a way to make this integral more difficult, right? I'm trying to show you some tricks to save you some labor. Sometimes it's not avoidable, right? Sometimes you just got to do the integration. Like these problems where you've got a plane bounding an octant or something and you're trying to calculate the volume over this like tetrahedral kind of area volume. There's not much to do. Those you just have to, I mean, it's just work. You can't avoid the difficulty. But sometimes these ones that are based on coordinate change have some kind of nice integration stuff that happens like that. Look for integrals of sine or cosine over whole periods. Once you see that, and if you have the integral from 0 to pi to 2 pi, right, you don't have to write more. But you have to be careful how you apply this, right? You can't get carried away. Make sure you don't miss terms that don't go to 0 like this. Right? Just because there's a cosine one place, like there was a cosine multiplying everything here, right? That didn't mean the whole thing went to 0, did it? That's right, and that compensates. All right, well, I'll see you guys tomorrow. Thank you.